This is your presenter Asloob Mudassar, and I am presenting slide number 139 of the course on laser physics. Question is, what are chemical gas lasers? Discuss at least one important laser of this category. The answer is, in chemical lasers, normally two gaseous elements react in either associative form or dissociative form to generate a molecule which is excited to some vibrational rotational level by the exothermic energy released in either the associative or dissociative reaction. The reactions are respectively given by A plus B gives you AB. The second reaction is ABC gives you A plus BC. The first reaction, that is A plus B gives you AB, is an associative form, and ABC, which dissociates, will give you A plus BC, is a dissociative form of the reaction. A and B, here A and B in reaction number 1, A and B could be in atomic form or the molecular form, or one could be in atomic form, the other could be in molecular form, and AB is a molecule which is in the excited state, and this ABC is a molecule which dissociates to give you A plus BC, where BC is a molecule and A could be in atomic state or in the molecular state. So these are the two reactions. In equation number 1, the AB molecule is excited to some vibrational level, and through the VV transition, that is the vibration to vibrational transitions, lasing action is achieved. In the second reaction, that is in equation number 2, the exothermic energy either appears in the excitation of the atomic species A to some electronic state, or the excitation of the molecule BC to some vibrational state. So you see that in equation number 2, this A, which the products of this dissociation are A and BC, where A could be an atomic species excited to some electronic state, and BC is a molecule excited to some vibrational state. The de-excitation of an excited vibrational state to a lower vibrational state produces lasing action. So you see that in these types of reactions, we are going to obtain our lasing reaction, which is due to the de-excitation of an excited vibrational state to a lower vibrational state, and that will produce the lasing action. Thus, according to equation number 1, AB is the excited form, acts as the lasing material. So in equation number 1, AB, which is an excited form of the molecule, will act as a lasing material. And in equation number 2, BC is the excited form, acts as the lasing material. So here is AB is the excited material which is in the form of excitation, and BC is a molecule in the form of excitation, and BC will also act as the lasing material. So AB in equation number 1 and BC in equation number 2 on the right hand side will act as the lasing materials. Some lasers are based on equation number 1 while others are based on equation number 2. And it is also possible that in some chemical lasers, these two reactions will occur simultaneously. So both actions could be present. Hydrogen fluoride HF and deuterium fluoride DF lasers fall in the first category. That is, they obey equation number 1. That is, they combine, that is A and B will combine you to give you A and B, AB. So A plus B will give you AB, and that happens with HF and DF lasers. Laser emission by the excited iodine produced in the exothermic dissociation of CH3I falls in the second category, because in the second category we have the molecule CH3I which dissociates and will give you the emission and will give you the laser emission. So laser emission by the excited iodine produced in the exothermic dissociation of CH3I falls in the second category. The dissociation of the molecule CH3I is through the UV light obtained from a flash lamp. Molecular hydrogen H2 and the atomic fluorine F are combined to produce hydrogen fluorine HF. So you can read this as hydrogen fluorine and deuterium fluorine. It produces 2.7 to 2.9 micrometer radiation. Highly toxic fuels such as NF3 or SF6 are combined with the hydrogen produced by some hydrocarbons. So hydrogens are produced by some mechanism, for example, maybe by some hydrocarbons, and they are combined with with NF3 or NF6 to produce the atomic fluorine. So atomic fluorine can be obtained from NF3 or SF6 by combining them with the hydrogen gas. Chemical oxygen iodine laser, abbreviated as COIL. Chemical oxygen iodine laser, abbreviated as COIL, emits 1.315 micrometer wavelength Cl2 gas and aqueous mixture of the hydrogen peroxide, that is H2O2, and the potassium hydroxide KOH are combined to produce excited oxygen molecule. These molecules react with the iodine molecule I2 to produce the laser medium. The laser medium is passed supersonically through the expansion nozzles, and the mixture thus passes through the laser cavity transversely, and the laser beam at lambda is equal to 1.315 micron is generated. The schematic diagram of the coil is shown in figure number 1. So let me show you that figure first. This is the figure of the coil, and the caption of the figure is schematic diagram of a chemical oxygen iodine laser system. In this laser system, you see that we have the chlorine gas, and then we have the KOH, potassium hydroxide, plus H2O2 in the liquid form. They are combined to give you the and of course the Cl2 gas is also combined with them to produce O2 gas generation. And with the O2 gas generation, that is the generation of the oxygen gas, heat is produced and KCl as a salt is also produced. And we are concerned with the production of the oxygen atom. So this oxygen this oxygen molecule is combined with the iodine gas, and then through the supersonic mixing nozzle, the laser medium is generated between the two laser cavity mirrors, and the material flows transversely through across the cavity. And then of course a laser beam with a wavelength of 1.315 micron is produced, and this is in the gray is the laser medium. So the laser medium, after after traversing the laser cavity transversely, will go to the exhaust portion of the system. So this is the structure of the coil system, which we are going to explain in the next paragraph. So chemical lasers are famous for generating high output powers in either CW, continuous wave mode, or the pulsed mode. Application area is high energy laser weapons for military use. Hydrogen fluorine is the most discussed chemical laser, and its detail is given next. So you see that we are going to discuss the hydrogen fluorine. That is the chemical laser of this type, that is the hydrogen fluorine, will be discussed next because it is one of the most popular of its type. Hydrogen fluorine lasers. In a hydrogen fluorine laser, excited hydrogen fluorine, that is HF molecule in the excited form, which we are representing it by the star. So HF star, which means that HF molecule is in the excited state, is required as the laser material. HF star can be produced through the following reaction. That is, we have the fluorine in atomic form combined with the hydrogen atom. Hydrogen molecule will produce HFO in the HFO molecule in the excited form plus atomic hydrogen, as shown in equation number 3. For this reaction, fluorine in the atomic form, that is capital F, is required, which is denoted by SF6. So it should be denoted by, not denoted by. So which is denoted by SF6 in a mixture of H2 and He. Let me read again. For this reaction, fluorine in the atomic form is required, which is denoted by SF6 in a mixture of H2 and helium. The inert SF6 is dissociated through the electric discharge, and a certain amount of atomic fluorine is produced, which reacts with the molecular hydrogen to produce the HF molecule in the excited form, that is HF star. Atomic hydrogen produced in the reaction of equation number 3 can react with the fluorine molecule as given. So you see that hydrogen in the atomic form is produced in equation number 3, which can react with the fluorine with the F2 molecule and can produce the same molecule in the excited form, that is HF in the excited form plus fluorine in the atomic form. And this fluorine can again be used as in equation number 3. And the hydrogen produced in equation number 3 can be used as in equation number 4. So this is a cyclic process. So the hydrogen can be used in equation number 4, and in equation number 4 the fluorine which is produced can be used in equation number 3. Atomic fluorine produced in equation number 4 can contribute in reaction given in equation number 3. The reactions given in equation number 3 and equation number 4 repeat in cycles. The two reactions produce a significant amount of hydrogen fluoride in the excited form. The energies produced in the two reactions per one molecule of hydrogen fluorine in the excited form are delta H1, which is equal to 31.6 kilocalories per mole, and delta H2, which is equal to 98 kilocalories per mole respectively. These energies are stored in the vibrational energy of the hydrogen fluorine molecule in its excited form. So let me read the last two sentences. So the two reactions produce a significant amount of hydrogen fluorine in the excited form. The energies produced in the two reactions per molecule of the hydrogen fluorine in the excited form are delta H1. So in the first reaction we obtain delta H1 is equal to 31.6 kilocalories per mole, and from the second reaction we have delta H2 is equal to 98 kilocalories per mole respectively. These energies are stored in the vibrational levels of the hydrogen fluorine molecule. Assume that all the energies released in reaction number 3, that is delta H1, is stored in the hydrogen fluorine molecule. The lasing action is the de-excitation of the hydrogen fluorine excited molecule, which produces a lambda of the order of 3 micrometer. That is lambda approximately 3 micron, which has energy equivalent to delta E1 is equal to 0.414 electron volt. The number of vibrational states, that is the vibrational quantum number occupied by the hydrogen fluorine molecule, is found as, that is the value of V vibrational level is equal to delta H1 over delta E1. If you produce these values, delta H1 also represented in electron volt and delta E1 is already in electron volt. If you substitute these two values over here, you will get V is equal to 3. This means that the hydrogen fluorine molecule in the excited form could be in any of the possible vibrational states, that is V is equal to 0, 1, 2, 3. So any of these states could be occupied by this hydrogen fluorine molecule in its excited form. If we choose that there are 36 hydrogen fluorine excited molecules, then the relative numbers n as a function of v of their existence are shown in part A of figure number 2. So let's move to the part number 2, part number A of figure 2. First, read the caption. Let's read the caption first. Pumped vibrational levels of the hydrogen fluorine molecule with a relative population shown in part A, for example, corresponding to reaction number 1. You have delta H1, you see that indicated over here. And the vibrational levels, the 4 vibrational levels are indicated. V is equal to 0, V is equal to 1, V is equal to 2, V is equal to 3. And of course, the value of delta H1 is also specified over here, 31.6 kilocalories per mole. And you know that this figure, that's part number A, is relevant to equation number 139.3. So that is equation number 3. And you know that n of V is actually distributed over here. We have started with assuming that there are 36 hydrogen fluorine excited molecules. So if you have 36 hydrogen fluorine molecules, and if you pump those molecules, these 36 hydrogen fluorine excited molecules will occupy these states in the following way. That is the vibration level. In the vibration level, there will be 2 excited hydrogen fluorine molecules. In the vibration level number 1, there will be 4 molecules. In vibration level number 2, there will be 20 molecules, and in vibration vibration level number 3, there will be 10 hydrogen fluorine excited molecules. So this that is n of u will give you the number of excited hydrogen molecules according to the number of levels they occupy. So we have the 4 levels, and this is the distribution of the hydrogen fluorine excited molecules in these levels occupied when the pumping is done to excite the hydrogen fluorine to its excited version, which is the hydrogen fluorine star. So this is the distribution which is given. Okay, now in the next one, in V is equal to 3, hydrogen fluorine excited molecule takes all the energy delta H1. And in V is equal to 2, you can see that the energy is also specified over here for the level V is equal to 3. So V is equal to 3 is the level that corresponds to the energy difference of delta H1. So in V is equal to 3, the hydrogen fluorine molecule in its excited form takes all the energy delta H1, and in V is equal to 0, the energy delta H1 appears only as the kinetic energy of the colliding partners. The transition V is equal to from V is equal to 2 to V is equal to 1 is the most probable. So the transition from V is equal to 2 level to the V is equal to 1 level is the most probable transition, because during these transition, because for this transition it produces the most intense laser beam. So it means that this is the transition from V is equal to 2 to V is equal to 1 is the most producing most intense beam, is the most probable reaction. So the transition from V is equal to 2 to V is equal to 1 is the most probable. Now for the second reaction given by equation number 4, we have V is equal to delta H2 over delta E2. So again, if you specify delta H2 in electron volt, and delta E2 is again equal to delta E1, and if you substitute these values and divide, you will get 10, because here we are using that delta E2 is equal to delta E1. The relative population n as a function of v, that is the population distributed in different vibrational levels, and here we are talking about that there would be 10 vibrational levels starting from v is equal to 0. In principle there will be 11 vibrational levels. So let's consider that there are 314 hydrogen fluorine molecules which have been excited. So 314 hydrogen fluorine excited molecules will be distributed in different levels, in different vibrational levels. So in the first 10 vibrational levels, the distribution is shown in in part number B of the figure. And you see that delta H2 is the energy which is taken by the vibration level number 10. And this is I have shown a total 11 vibration levels starting from V is equal to 0 to V is equal to 10. And this is the distribution of the hydrogen fluorine molecules in these levels. This is the population distribution, or you can say that the relative population distributions, because we have assumed that we have a total of 314 hydrogen fluorine molecules which we have excited through the pumping, and they will occupy the vibrational levels according to the part B as shown in part number B. For example, V is equal to 0 level will have 12 hydrogen fluorine excited molecules. Similarly, V is equal to 1 will have 12, and so on. The maximum number is 66, which is in V is equal to 5 vibrational level. And you see that this level corresponds to equation number 4, where delta H2 is equal to 98 kilocalories per mole. And these two scales are, and these two diagrams in part number A and part number B are not to the scale. So they carry different scales. In part number B, the vibration, the transitions from V is equal to 5 to V is equal to 4 is the most probable. So from V is equal to 5 to V is equal to 4 is the most probable transition because it produces the most intense beam. In the presence of both reactions. So you see that here we are now talking about both reactions. Before that, we have talked about the reaction number, equation number 3 and equation number 4 separately. Now, if in the presence of both reactions, hydrogen fluorine is excited to several vibrational levels. When hydrogen fluorine excited molecules are confined within a laser resonator, lasing action on several wavelengths can occur. The interaction potential of the hydrogen fluorine molecule is n-harmonic, and the vibration levels are not equally spaced. Due to this, the laser spectrum is quite wide, and lambda could range from 2.7 micron to 3.3 micron. So you see that here I have shown that these levels are equally distributed. That is, the vibrational energy levels are equally distributed. But in principle, due to the interaction potential of hydrogen fluoride having a type of n-harmonic potential, the vibrational energy levels are not equally spaced. One of the reasons is the same cascading process which occurs for the carbon monoxide laser and which we have discussed in the previous slide, that is in slide number 138. For example, in the strong transition from V is equal to 2 to V is equal to 1 in part A, the level 2 will deplete, whereas the population will accumulate in level number 1. The level number 2 will act as the lower laser level for the transition from V is equal to 3 to V is equal to 2, whereas the level 1 will act as the upper laser level for the transition from V is equal to 1 to V is equal to 0. The second reason is that the partial inversion can exist in the rotational levels belonging to the same vibrational levels. The schematic diagram of this continuous wave hydrogen fluorine laser configuration is shown in figure number 3. So having explained the cascading process, I am going to show you the continuous wave hydrogen fluorine laser configuration depicted in figure number 3. That is this. So first the caption, schematic diagram of a supersonic diffusion hydrogen fluorine chemical laser. You can see that this is the arrows indicate the dissociated fluorine from jet heater. So using the jet heater, the fluorine in atomic form is produced, and you see that it is flown in the direction of the arrows. So this is the dissociated fluorine from the jet heater. And H2 injection through perforated tubes. So these are the perforated tubes, and here we inject hydrogen molecule, hydrogen gas. And you see that the cooling pipe is circling around these jets, and cooling is produced. You see that the cooling pipe is coming out from here. And actually these are the expansion jet nozzles. These are the expansion jet nozzles. This is the laser cavity, one mirror of the laser cavity here, and the second mirror of the laser cavity is shown over here. And you see that you have a laser medium in between them, which is being pumped through the transversely across the laser cavity using expansion jet nozzles. And the explanation of this one is given in the text, which I am going to present now. Fluorine is thermally dissociated. That is, through the heating process, fluorine is thermally dissociated in a heating assembly and then expanded by expansion nozzles to supersonic speeds. H2 gas is mixed at the nozzles by perforated tubes inserted in the expansion nozzles. Hydrogen fluorine excited molecules are produced and ejected through the expansion nozzles with appropriate diameters and are made to flow orthogonally to the axis of the unstable resonator. Due to the high power generation, cooling of the metallic mirrors is done through the water cooling process. Such a system can produce optical power in megawatt ranging during the CW operation, but with poor electrical efficiency. So these systems have poor electrical efficiency, but if it is a matter of optical power, then these produce a tremendous power in the range of megawatts. Pulsed hydrogen fluorine lasers use a T-type configuration, which has been given in slide number 138 and figure number 9 thereof. The waste products, so you see that the problem is with the waste products. The waste products produced in the T hydrogen fluorine lasers are difficult to dispose of, and in some cases production of atomic fluorine can be explosive. These two factors limit the commercial use of hydrogen fluorine lasers. Chemical lasers, due to their tremendous power, can be used as directed energy weapons to destroy missiles. Deuterium fluorine lasers have wavelengths with good transmission through the atmosphere. Deployment of hydrogen fluorine and coil systems on dedicated airplanes to destroy enemy missiles has been demonstrated. Application areas is the high energy weaponry for military use. Deuterium fluorine, hydrogen chloride, and hydrogen bromide are equally important chemical lasers covering an overall range of 3.5 to 5 micron. So this is the end of slide number 139.